Hi everyone, welcome to Mostly Math. Let's consider an infinitesimal right triangle. We've got sides dx, dy, and ds. We know from the Pythagorean theorem that ds squared is simply equal to dx squared plus dy squared. This is actually what we are going to be considering the definition of flat space. But let's go ahead and talk about an equivalent description. Polar coordinates, you may have heard of them. Let's go ahead and consider transformation x equals r cos theta, y equals r sine theta. In this case, if we take differentials of both sides, we'll obtain the following. dx is equal to r, sorry, I want to do the dr's first. Cosine theta dr plus, did cosine theta. Great. R minus sine theta d theta. Just want to make sure you get all the signs right. It's very important. And then dy is equal to sine theta dr plus r cos theta d theta. We're just going to go ahead and plug these expressions into our Pythagorean theorem here. See what we get. Cos theta dr minus r sine theta d theta squared plus sine theta dr plus r cos theta d theta squared. Expand this out. See what we get. Okay, sounds good. Just expanding this term first, we'll get cos squared theta dr squared minus 2r cos theta sine theta dr d theta plus r squared sine squared theta d theta squared. Similar term for the second one, plus sine squared theta dr squared plus, this time, 2r cos theta sine theta dr d theta plus r squared cos squared theta d theta squared. Notice we have an interesting trig identity. It's going to be involved in both these two terms here. Obviously the middle terms cancel out since they are exactly the same. Opposite signs. We obtain cos squared theta plus sine squared theta in two places. We get that here with the dr term, dr squared, and we also get that here with the r squared d theta squared term. Excellent. Now we simply recognize this is 1 from high school. So the entire expression, dr squared plus r squared d theta squared, should definitely be familiar to you. Probably may not have derived it in this way, but this is the length element for the polar coordinates, and you can also obtain the volume element from this as well. And notice that although it no longer looks like dx squared plus dy squared, it's still a description of flat space since we simply did a coordinate transformation of x and y to r and theta. All right, let's say we wanted to have different coordinate transformations plugged in. Well, we could do the same expression that we just did each time, but since it can get pretty tedious with the algebra and you might not always know what trig identity to use, maybe you might not even have a trig identity, it's important to generalize. So now we are going to be considering the following generalization. X is going to be some function of two new variables, u and v. In this case, we'll use the multivariable chain rule to show that dx is simply partial x by partial u du plus partial x by partial v dv. Excellent. We're going to let y be a function of the two new variables as well. So dy is the same thing, but just with x replaced with y. No problem. Now we're going to compute the arc length for a general coordinate transformation of two variables, just as before. We're going to be showing considering ds squared to be dx squared plus dy squared with our coordinate transforms. Dx by du plus dy by dy. Sorry, that does not make sense. I do apologize. Plus dx by dv squared plus the same thing with x replaced with y. I'm just using this notation to save writing. There's no need to write this out. It's exactly the same. Yep, good so far. This is now simply partial x by partial u squared du squared plus 2 cross terms x by u and x by v du dv plus partial x by partial v squared dv squared plus the exact same thing with x interchanged with y again. And now we're going to explicitly write out the final line here. Just add that extra line there as well. Final solution is going to be dx by du squared plus dy by du squared. See, we just did the same thing with x replaced with y. Du squared plus 2 times the cross terms x by u, x by v, plus y by u, y by v. Got one more term, the v terms, x by v squared plus y by v squared dv squared. Sorry, I forgot the du dv here. Okay, this is our final answer. So for two arbitrary coordinate transformations, x and y are now functions of two variables, u and v. This is what we would get for dx squared. Pretty complicated. It is not really illuminating, and we didn't just do all this work to get a strange formula. We actually have to use it. So let's go ahead and apply it to a special case. We'll be considering a coordinate transformation that you probably haven't seen before, but it's pretty straightforward and is a good illustration of the power of this formula. Let's make sure I have this right first. Yep, looks good. We'll be considering the following coordinate transformation. X to be the new variable u plus v, and y to just be the variable v. Pretty straightforward. And first, let's compute the Jacobian of the transformation. It's just basically notation here. I just don't want to write all the partial symbols, but in general, the Jacobian is very useful for computing anything in coordinate transformations. You're going to eventually have this, but this means we're going to be considering a matrix where the rows are the function and the columns are which variable you take the derivative with respect to. So for this coordinate transformation, first entry is going to be dx by du. Well, that's just one. Next entry is dx by dv. Sorry. Also 1. Next entry, dy by du. This one is 0. And last entry is going to be dy by dv. This one's 1. And basically, the entire essence of the coordinate transformation can be seen from this matrix. We already see we have some off-diagonal elements, so perhaps we should be expecting an off-diagonal element to be in the arc length as well. Let's see if we obtain that. All right. Using our formula below, ds squared is equal to dx by u. That's just 1 plus dy by u. That one's 0. Du squared plus 2 dx by u. 1, x by v, 1, y by u, 0. Okay, good, done with that. And last term, we have x by v, which is 1. And we also have y by v, which is 1 as well. Simplifying this, we obtain our final result, du squared plus 2 du dv plus dv squared. And we do see that we have an off-diagonal element here. This is interesting because we just had a coefficient multiplying one of the differentials before. We have that again with a 2, but we also have an off-diagonal element, which means upon first glance, you might not think that this is a flat metric. In fact, it is. And in general, we can't tell if a metric is flat simply by looking at it. For that, we need something called the Riemann curvature tensor, which is very important in studying differential geometry and also general relativity as well. And I might cover it in a future video. If you want to see more, definitely feel free to subscribe. Be seeing you next time.